to the class. So we're going to talk about area of a parallelogram. And this is really important because on the previous page, we talked about the magnitude of the cross product between two vectors. This kind of goes hand in hand with that, right? And this is actually a geometric representation of that concept. It also has a lot of applications, so it kind of works out nicely. So if we're looking for the area of a parallelogram, we're doing it with the idea that there is a geometry rule that allows us to figure out those values. Right? So the area of a parallelogram is the same as area of a rectangle, base times height. All right. Now you see in the diagram there, we have a fairly well labeled diagram. The issue is that magnitude of v sine of theta seems to come out of nowhere. All right. So what I'm going to do is I'm just going to kind of zoom in and pretend that that's not there, at least for the time being. All right. So this side here, if I can get my highlighter in tune with my speaking. This side here is the height, right? And it's the height of a right triangle. Also the height of the parallelogram, aka the thing that we would need to know. But more importantly, because it's the height of the right triangle, rules of SOHCAHTOA come into play. All right. So what I have here is the sine ratio, because I'm given that value theta. Sine of theta would be equal to the opposite side, which is the height, over the hypotenuse, which, yeah, the hypotenuse is represented by vector v, but its length is actually the magnitude of v. All right, so the vector itself is v, but its magnitude represents the length. All right, just like the length of this side would be the magnitude of u, but the vector itself is u. All right. Now, to get the height of this parallelogram, I would just need to solve for h. So cross multiply, get h is equal to the magnitude of v times the sine of theta. So that's where, I mean, it's really just the justification for where that expression, the magnitude of v sine theta, came from. Because it kind of comes out of left field. It's like, well, how do you know to label it that? That's the explanation. But now that we have that, we actually have enough information to say what the area of the the parallelogram would be, because the entire base would be this green highlighted piece here. That has a length that is the magnitude of u. All right. Now the height, again, which is that orange piece, we can now say is equal to the magnitude of v times the sine of theta. All right. Now, reflecting back to the previous page, we can see, without actually flipping there, that this is the rule by definition, right? So this is equal to u cross v magnitude, right? So the magnitude of u cross v, right? However it makes sense to come up with that, they're one and the same, right? So what we get from this is that the area of a parallelogram, regardless of the space, a parallelogram is a two-dimensional figure, but you could have a two-dimensional figure in three-dimensional space, just a matter of orientation. And so if we could figure out the magnitude of the cross product between two adjacent vectors within that parallelogram, then we would be able to figure out the area of that parallelogram. Right? It also kind of gives us a little bit of a clue as to the true meaning behind a cross product. So what we're getting from this is, geometrically, the magnitude of a cross product is the area of the parallelogram formed by those two adjacent vectors in that parallelogram. All right. So let's look at an example here. Number 7, find the area of the parallelogram PQRS with these vertices. Now, drawing this out by hand could be kind of cumbersome. Also, with a touch screen, GeoGebra, it's also kind of a pain. So it's 6 of one, half a dozen of the other at this point. What I'll do is I'll kind of mix and match strategies. I'll show you how to do it by hand. Then I'll actually use the laptop, GeoGebra on the laptop, to be able to kind of walk you through the rest of it. All right. So we need a 3-dimensional graph, which is really not anything more than just a perspective drawing of the X, Y, and Z axes. All right. So 1 in the direction of X. So for point P, 1 in the direction of X, 1 in the direction of Y, but no elevation in the direction of Z. So if I want to plot this, I'm taking 1 step towards X, 1 step towards Y, but I'm not elevating from there. So I'll plot a point. We call that point P. Now the next one has the same general structure, except we're going out 7 units in the X direction. So that's going to put us about right here. And that would be point Q. All right, so those are 2 sides of the parallelogram, PQRS. Now, generally, the way a parallelogram is named is the order in which the points should be connected. I mean, that's actually a rule of thumb. That's how it should be. Not everybody adheres to that, but that's how it should be. That's actually the relationship. So R, 9, 4, 2. All right, so we're going to go out 9 in the direction of X. So it looks like I need more X. Then I want to go out 4 in the direction of Y. So 2, 3, 4. All right, so just kind of eyeballing it. So that's 9, 4, but then I got to elevate a height of 2, right? So just kind of roughing out what 2 might look like in terms of Z. That's roughly 2. I'm going to go up that distance. Oh, that was weird. Kind of taking off on me. I might have to zoom in a little bit. Let me do it on this side. Yeah, there we go. That's one of those cases where maybe a little low-tech approach might be the way to go. A little index card, that kind of deal. But that's where point R ought to be. And if we connect that with point Q, because that's next in line, PQR, it's elevating our parallelogram, right? So the next one would be S. Actually, as it turns out, we don't really need it, but we'll plot it anyway, because 3, 4, 2, that's saying go out 3 in the direction of X. Because all we need are 2 adjacent vectors. And so we can actually get what we need from this, but we might as well go the rest of the way. So 3, 4, and then the same distance up from there. So I'm going to bring it in. And it's something like that. you know, it's a hand-drawn sketch, so it's not going to be perfect, but it gives you an idea that one side of the parallelogram is on really the floor, and you kind of elevated the other side. So you just imagine a piece of plywood, you know, rectangular plywood, right? A rectangle is a form of a parallelogram, so that works. And you're just, you and a friend maybe are holding up one end of it, where the other end is resting on the floor. So it's creating a ramp. That's essentially what it's looking like. If you're holding it 2 feet off the floor, it would kind of get the job done in terms of a visualization, right? So we got to do math to this though, right? So we got to decide what we want the vertex to be, but that's all right, because any of the 4 points can be the one that we pin to the origin. It just makes sense to pin the point P to the origin. So what I'm going to do is I'm going to work off of point P and displace outward from there towards Q and S. All right, so I'm going to be finding vector PQ and vector PS. Originally, we had, when we didn't plot point S, we had P, Q, and R. In that case, I would have done Q, P, Q, R, but now we have all 4. It's fine to go with whatever pairing of values you want to go with, as long as they have a common point. All right, so from PQ, we want to find the displacement vector. So from PQ, 7 minus 1, 1 minus 1, 0 minus 0. So 6, 0, 0. All right, so that would be vector PQ. That would get us from P to Q if P was at the origin. All right, so really that's just saying we're taking 6, to get from P to Q, we just need to take 6 steps along X and that's it. All right, from P to S, 3 minus 1, 4 minus 1, 2 minus 0. So 2, 3, 2. All right. So now we have a couple of possibilities here, because if I want to find the area of this parallelogram, I can find the cross product between PQ and PS and then find the magnitude, or I could use the magnitude of the cross product formula, but that requires me to find the angle separating PQ and PS. All right. So it really doesn't matter which way you go. We haven't really done too much with the magnitude of the cross product formula, so we might as well do it that way. So the first thing I'm going to do is solve for the angle theta. All right. So I'm going to, now that I'm done with this diagram, I'm going to shrink it down and put it in the closet over there. Create some space. All right. So if I want to find the value of theta, so the angle separating these 2 vectors, theta would be equal to the inverse cosine of the dot product separating PQ and PS. Well, dot product of PQ and PS. Divided by the magnitudes multiplied. All right. So since we got to figure out the magnitudes, might as well just do it off on the side here. PQ has a magnitude, well, it's just 6. It's 6 steps in the direction of X, and that's it. So that's easy enough. We don't have to do any crazy computations there. The magnitude of PS (2 squared plus 3 squared plus 2 squared under the radical. So, thought I heard something. 4 plus 4 is 8, plus the 9 is 17. right? So we got root 17. We also need the dot product of the two. That's easy enough though, because PQ dotted against PS, you're only really multiplying the first two values because everything else zeroes out. So that's just going to be a 12. That's actually kind of nice. So my theta is going to be the inverse cosine of 12 over 6 radical 17. Which simplifies, even though we're going to do it in calculator work, might as well simplify what we're going to put in the calculator. So 2 over radical 17. All right. So that'll give us our theta. I don't want to put that in just yet because it's not going to be very appealing and we'll have to do some rounding. So we're just going to sit tight on that. If I want the area of the parallelogram, I'm looking for the magnitude of the cross product between PQ and PS, which is going to be the two magnitudes multiplied by the sine of theta, right? So by the sine of, we just discovered that theta is equivalent to the inverse cosine of 2 over the square root of 17. I'm just going to chuck that right in. Rather than finding the decimal equivalent to that, it just kind of makes sense to just pop that right in because this is going to be our theta. We already know what magnitude of PQ is. That's equal to 6. Magnitude of PS, we already know that that's equal to rad 17. So it's really just a matter of chucking all this stuff into the calculator and getting our results. So it's going to be 6 times the square root of 17 times the sine of the inverse cosine of 2 over the square root of 17 close it up, hit enter. You know, it's an ugly computation, but at least we'll get the most accurate answer that we can get without having to go too crazy. So about 21.6. They didn't give us any units here, so it's an area. You know, we just want to be mindful of the fact that we could be given units, in which case we would say unit squared. You know, whatever the units are that you're given squared. But in this case, since we weren't given units at all, we would just say unit squared, like generic unit squared. But if it's meters or something like that, meters squared, miles squared, square miles, you get the idea. All right. So, you know, there's a fair amount of stuff going on there, but it's not too bad as long as you kind of follow the recipe. You could have deviated significantly. You know, like everything I did in blue is going to be the same no matter what you do. But everything I did after that is dependent on what approach you want to do. Because if you found the cross product between PQ and PS, which actually would be pretty easy because there's a couple of zeros in there, then just find the magnitude of that, you'd get your answer. But like I said, we hadn't done or used this formula together, so I figured it was worth the time a little bit. All right. Number 8 is an interesting question because it talks about the area of a triangle, and you're like, well, we know the area of a parallelogram, but we haven't talked about area of a triangle. How are we supposed to know how to do this? Well, the answer is cut a parallelogram in half and you have a triangle. All right. If you think about this rule here, base times height, and you think about the area of a triangle, which is half the base times the height, then you kind of have what you need, right? So if we're looking at area of a parallelogram as base times height, base times base, no, base times height, then area of a triangle, which is half of that, would be, you know, if we're going with generic U and V, cross product of two vectors, the magnitude of those, and we would just be saying 1/2 of that result would give us the area of a triangle, all right? So it's really just that 1/2 relationship. So then the big question would be, okay, well, what's U and what's V? Well, that U and V is still going to be we're still going to be looking at that as two consecutive sides of a parallelogram, right? So I would be looking at this triangle. I'll come back to the writing in a second, but I'd be looking at this triangle and saying, all right, well, how could I make this into a parallelogram? And we could take these two sides, move one here and one here, and now we have a parallelogram. See if it'll autocorrect the way I want it to. Yeah, there you go. So there's your parallelogram with consecutive sides PR. I'll make that one vector. And PQ, I'll make that another vector pinned at P. So I'd be looking for PR. I'll do PR first. And PQ. So displacement vector is a lot simpler because these are, even though it's written as a perspective drawing, these are unit vectors in the direction of X, Y, and Z. So this is I, J, and K. So it's actually pretty simple. When I do PR, it's 0 minus 1, okay, so -1. 0 minus 0, 1 minus 0. So 0 and 1. And then PQ, 0 minus 1, -1. 1 minus 0 is 1, and 0 minus 0 is 0. All right, so if I'm looking for the magnitude of the cross product here, I might consider, I mean, you could go either way with this one. I might consider doing it by finding the cross product because I don't think that's going to be difficult. But then again, the computations necessary to find the angle between the two vectors, that's not going to be difficult either because of the prevalence of the zeros and ones, right? So, but because the last problem I did using the shortcut, quote unquote, shortcut formula, magnitude of the cross product formula, this one I'll do it by finding the cross product, you know, because it doesn't hurt to review that anyway, right? So if I want to find the crossing of PQ and well, I'll do PR first. We're going with absolutes anyway, so it doesn't matter, but just to keep it consistent in the way that I wrote it, I'll do the PR first. So IJK, -1, 0, 1, -1, 1, 0. All right, so just remember, it's going to be 2 by 2 square matrices as coefficients of I, J, and K. I knew there was a video I forgot to make. Not a big deal, but I said I would do it, and I feel bad when I say that I'm going to do something and I don't do it. The derivation of the cross product formula. I'll take it as a typo. If somebody wants to send me a reminder, derivation of cross product formula, I'll take that as a typo for bonus credit. Right. So we disregard the row and column that contains the unit vector, the relevant unit vector, in this case, the I. So you pretend it's not there. We have 0, 1, 1, 0. Do the same thing with the J, -1, 1, -1, 0. And then same thing with the K, -1, 0, -1, 1. -1, yeah, 0, -1, 1. Looking at the wrong thing. All right, just double checking. Yeah, all right. Then to find the cross product, we're multiplying down the main diagonal. So it's diagonal down minus diagonal up. So diagonal down, 0. Diagonal up, 1. Subtract the 2. Make that the coefficient of I. Diagonal down, 0. Diagonal up, -1. Subtract the 2. We got that negative that's coming down for the ride here. That's the coefficient of J. Diagonal down, -1. Diagonal up, 0. Subtract the 2. That's the coefficient of K. So -I. We got lots of cancellations here. So 2 negatives make a positive, but then it gets negated again. So -J. And then we have -K. So it's actually negative, negative, negative. Right? To get our cross product. Some people don't like doing or finding the magnitude of the cross product using this technique, just simply because it's, the negatives and, all that stuff getting confusing. They'd rather just do it the other way because it's more procedural. That's understandable. Sometimes I'll do it both ways just so I don't confuse myself, let alone the rest of you. All right, so then that's giving me the magnitude, that's giving me PQ crossed with, PR crossed with PQ. I keep wanting to say that the other way around. I want the magnitude of that. Which is the component squared. So -1 squared plus -1 squared. It's really 1 squared plus 1 squared. -1 squared under a radical. Result result radical 3. Now, that would be the area of the entire parallelogram, right? Finding the magnitude of the cross product gives you the whole shebang, the whole thing. I only want the area of the triangle. I only want this part. So I'm going to chop that in half. The area of the triangle would then be radical 3/2. All right, so then we'll just chop this down over here. So therefore, area of the triangle would be 1/2 of that radical 3, or radical 3/2 square units. All right. So it definitely takes a little doing. It's not the simplest process in the world, but it's definitely doable. But as we've come to understand, there's always a shortcut. So let's get to that. Using the determinant to find area. When you find the determinant of a 2x2 square matrix, you are in fact finding the area of the parallelogram that's created by the 2 adjacent sides determined by the vectors that make up the rows or columns of the matrix. Right? In short, if we need to determine the area of a parallelogram, we need only to find the two vectors that correspond to adjacent sides of the parallelogram and compute the determinant. The issue with this is this technique only works in 2 space, but it's still something. All right, and so this allows us to use a little touch of linear algebra to determine the area without having to go nuts over this stuff. Right. So if I want to find the area of this parallelogram, and we could just do a quick sketch. I don't think it's too crazy, because in 2-dimensional space, it's really pretty straightforward when we want to come up with vectors. Actually, I could even do it by hand. 1, 2. And then negative 3, 4. It's looking something like this. If these two vectors come together to form a parallelogram, just like any kind of vector addition would tell us, what we're getting from this is that the determinant between these two vectors, the determinant of a matrix with these two vectors as columns or rows, would accomplish the same thing. All right, so we have, again, U and we have V. If I find the determinant, I'm going to use my line draw tool here, determinant 1, 2, I'll make them column vectors. So I'm doing U down the main column. I'm going to do it both ways just so you see how it works. V down the second column. Or we could do it with U as a row vector, 1, 2. With V as the second row. The reason I'm showing this using both methods is, well, not just to show the commutativity of it, it's also so that it kind of answers the question for those folks who have some experience with linear algebra, and that is, why did we do everything with column vectors in linear algebra, but now everything's a row vector here? And the short answer is it never mattered. It's just in linear algebra, for some reason, we focus on the columns more than we focus on the rows. It has to do with the linear combination component, but that doesn't mean a lot to a lot of people, so it is what it is. All right, so the determinant of UV, diagonal down minus diagonal up, 2 by 2 square matrix, so it's the same relationship, 4 minus negative 6. Diagonal down minus diagonal up, 4 minus negative 6. In both cases, 4 plus 6, 10, result of 10. All right, so in either case, we're looking at an area corresponding with those vectors, all right? And if you were to compute, you remember back in geometry or old school algebra, the way to figure out the area for something like this, they use plenty of different techniques, but the most popular one was that you encase it in a rectangle and then find the area of that rectangle and then subtract off all the excess, right? So, I dropped my Apple Pencil. So what you would have to do, or what you did back then, was you encase the whole thing in a rectangle. And you would say, okay, well, what do I get if I take off this triangle, this triangle, this triangle, and this triangle? Whatever's left would be the thing that you were looking for. So what I'm saying is what will be left will be an area of 10, all right? So let's flip the page and talk about the triple scalar product. Actually, I gotta pause the video real quick. Zoom. So yeah, so we're going to talk about the triple scalar product, and that's a way that we can find the volume, just in the same way that we found area using a 2 by 2 square matrix, finding the determinant. We can use this to find the volume in 3 dimensions, right? So this allows us to find, instead of the area of a parallelogram, we could find the volume of a parallelepiped, which is one of the things that you're focusing on in your technology assignment. All right, so it actually is the result of taking the cross product of 2 vectors, v and w, and dotting that against an additional vector, in this case u. But the shortest way, the shortcut approach to doing that, is to just simply find the determinant of the 3 by 3, right? So, and this one, we could do it by hand, but this could also be a linear algebra course, and it isn't, so we're not going to. We'll do it in the calculator. If we were to do it by hand, you would see a lot of similarity between this and the technique for finding the cross product, because when we find the determinant of anything bigger than a 2 by 2 square matrix, what we do is we break it down into cofactors that are 2 by 2 square matrices. So it's basically like we write it as a linear combination, a sum and difference of scalars multiplied by the determinant of 2 by 2 square matrices. So there's a lot to it, but it's actually pretty simple when you get into it, right? So the triple scalar product is actually the determinant, and it's the same idea as what I demonstrated on a previous page. If I put u, v, and w in as row vectors or as column vectors, it would still amount to the same quantity. So you'd be in good shape there. I.e., if you screw up and put it in the wrong way, you're still going to be all right. All right. So how do you do it? Well, you do it in Desmos. That's how you do it. So we go to Desmos. Beautiful, free math. Then I'm going to expand it a little bit. Under Math Tools, you click on Matrix Calculator. There's a little gray or rectangle there. I don't know why that's there. But you tap on New Matrix. We want a 3 by 3, so we'll up the rows and columns. 1, 3, 5, 2, -1, 0, -3, 0, -1. So that's our matrix. Just double check you type it in correctly. Hit enter to lock it in. And then very simply, DET for determinant of A, and you get a -8, right? So the determinant itself is negative, but that negative sign just implies direction, right? It's just generally giving a rotation, an indication of rotation from one vertex, from one vector to another, right? Informing the parallelepiped. It's a little easier to see in the form of a parallelogram. Just a question of, are you going from in a counterclockwise direction or clockwise direction to get from one vector to another? The same idea holds in 3 spaces, except it's not as simple as just going one way as opposed to the other, because you can go in a 3rd dimension. Bottom line is, we're going to drop the negative because all we care about is the absolute value. All right, so the volume should be an absolute value. And again, these were not given with any units, so this would be units cubed. All right. So if we wanted to, we could construct the parallelepiped, and you actually could, like after you complete the technology assignment, you're qualified to do that. You can create a parallelepiped and use that to determine the volume. Find the volume of that parallelepiped, and you'll see if it has these component vectors, you'll see that the parallelepiped that's generated would have a volume of 8, right? So then, I define the definition piece early in the week, obviously. But it essentially is just confirming that the volume of parallelepiped is the triple scalar product, or the determinant of the 3 by 3 square matrix, whose components are the 3 vectors of the 3 adjacent sides in the corner of a parallelepiped, right? So for the examples, numbers 10 and 11, it's really the same thing. It's just a matter of just doing what we did for number 9, which is put in the -1, the -2, and the +1, the 4, the 3, the 2, the 0, -5, and -2. and get the volume that way. Right, so it just unfortunately means you just got to do a fair amount of typing, but it's not the end of the world because you could have to do it by hand. You're like, well, how do we know it's difficult to do by hand? Well, the fact that you never have to find out, at least in this class, that's kind of the point. All right, so I got my matrix in, determinant, matrix A, this is -40, so my volume is going to be equal to the magnitude, the absolute value of -40, which is going to be 40 units cubed. And it's actually at this moment that I realized that in the case of, it's not wrong that I wrote it, but if I was talking about the volume in the previous question of a parallel pipette, then I would take the absolute value. Right, so the volume of the parallel pipette, but the triple scalar product in the previous question is actually -8. I just want to be clear about that. The volume of the corresponding parallel pipette is what would be 8 units cubed. Right, so same general idea here. It's just a matter of verifying that you put the values in correctly. You can put them in as columns or as rows. Either way, you're going to get a value. That value could be positive or negative. If it's negative, you ditch the negative sign because we only care about the absolute value. If it's positive, then you're already good to go. What do we got in the chat? Oh yeah, to get to the matrix. And in fact, I got to do the next one anyhow, so I'll just take it from scratch. So let's say we have a question that requires us to do a matrix. You go to desmos.com. Then it brings up, the regular website. You click on Math Tools, and you'll see Matrix Calculator. All right. Once you see that, I don't know where that gray rectangle is coming from, but you just tap on New Matrix, the blue rectangle. It brings up automatically by default 2 by 2, but you see below that it says Edit Matrix A. We want it to be 3 by 3. So you up the rows and columns just by hitting the plus sign. In the case of the next example, we want to input 205. I don't know what I just did there. 205. So 2 right arrow, 0, right arrow, 5 right arrow. Then 224. So right arrow, 2, 2, 4. And then the last one, 1, -1, 3. So right arrow, 1, -1, and 3. Right. So then when you hit enter, it locks it in. You're done editing that. Now all we want, those vertical absolutes that we put around a matrix, tells us it's really notation for determinant. But on Desmos, we just select DET, determinant, type in A, and it just spits out an answer. In this case, it's giving us a 0. All right. So what that's telling us is that this parallelepiped doesn't have any volume. All right. So you just kind of look at it like, well, all right, if you're talking about a cube, for example, if I told you that a cube had no volume, but it had area, the cube has area, but it has no volume. And you'd say, okay, well, is it because the height's equal to 0? Maybe it's got a length and a width, but no height. So in that regard, is it really a cube? Probably not, right? In the case of a triple scalar product, if you have 3 vectors, it's possible that those 3 vectors don't form appropriate adjacent sides of a 3-dimensional figure. Because if they're all pointing in the same plane, if they're all living in the same plane, then they wouldn't create something with depth or height to it. So if I want a parallelepiped, I would need something that has, you know, I mean, you got two vectors that are kind of pointing off in this direction, and then another one that's going off over here. And then from there, you could build out the rest of the way. That would create a parallelepiped. But if they're all kind of living in the same plane, and I'll just kind of, I'm doing it as a perspective drawing, so it's a little iffy, but, oh, hold on. Didn't put my line draw too long. So let's say that this middle vector is in the span of the first two vectors. Right? So they create a plane. Right? So I'm going to kind of scale this down a little bit. So you have something like this, copy. And so we're looking at a plane here. And this other vector, this little guy, is in the span of that plane, then it doesn't have any height to it. All right. But if you have something else, and actually now I'm not liking my other drawing, I feel compelled to draw it again. Just because now, shockingly, I successfully drew a picture. So now I'm kind of riding that high. I want to continue. All right. So maybe that third vector is not living in the plane, something like that. This would create a parallelepiped. The other one does not, but it's really just more importantly, the vectors are coplanar. All right, they're all living in the same plane. All right, so you'd be able to get some volume out of the other one, but not this one. You know, out of the second one, but not out of the first one. All right, so it's weird. It's interesting but weird. All right, so I'm gonna pause this or stop this video so that I don't have it too long.